All right, hey folks, we are continuing to learn more about Lewis dot structures here in part 3. Okay, so we're going to follow the steps for writing a Lewis dot structure from the formula as given in the guidelines that start on page 105. We've done this a couple times in this lecture, but here we're going to explicitly follow these steps to talk about what we're doing. Okay, so step 1 is to determine the total number of valence electrons in the molecule. So here we have an example of CCl4. And so the total number of valence electrons is 4 for the carbon, 7 for each chlorine times 4, which is 32. And we see it here pictorially with the symbols. So chlorine has 7 for each one, for a total of 28, plus carbon has 4, so we get 32. So we keep that number written down or off in our head, and then we determine, well, step 2, determine the central atom and place a single bond between the central atom and each atom bonded to it. So typically, the atom that there's like one of is the central atom, and then it has like the other things around it, right? So here in CCl4, carbon is the central atom, and so we just put carbon in the middle, and then draw a single bond. We're gonna assume single bonds unless if proven differently, connecting to each other atom. So this takes care of the 8 valence electrons needed to form 4 single bonds around carbon. Then, step 3. We need to calculate the number of remaining valence electrons and distribute them as pairs to the outer atoms to fulfill octets. Right, so we had 32 total that we needed. We've used up 8 by giving carbon its 4 bonds. So there's 24 valence electrons remaining. And so we would simply start putting pairs around chlorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So until we run out, or until all of the atoms have full octets. And that's step 3. Now step 4. If the central atom is short of an octet, turn non-binding pairs of electron bonds to make double or triple bonds. So we did this before with formaldehyde, and here's an example of C2H4. Okay, so here we're done, right? That's the final structure, because carbon is satisfied with 8, chlorines are each satisfied with 8, and we've used up the total of 32, so it's done. If it's not done, or if one of those things hasn't happened, we have some left over, or one of the atoms does not have a full octet, then we move to this step. And here we see, well, actually, let's just take C2H4. So here we have 2 carbon atoms actually as kind of a central backbone. And then we have 4 hydrogens, and we can put 2 on each carbon. Carbon is now, it's deficient though. It needs to share 1 more. So the last ones can share. We get a double bond. And so here we are back to the question, and we can see right that the pair, and here they've drawn them both over one carbon. We had it as one here and one here, but it's equivalent because there's basically two. They're just showing it as a pair, but ultimately that pair ends up being shared as a double bond, which satisfies both carbons. 5, which is check your work. Go back over and make sure everything looks good and makes sense and everything is happy and satisfied. All right, let's try a couple of our own here. So I wrote the guidelines at the top, right? Number 1, find the total number of valence electrons for all the atoms in the molecule. Determine the central atom and connect all other atoms to the central atom with single bonds. Subtract the number of valence electrons just used from the total and distribute the remaining electrons in pairs. If any atoms are short of 8 electrons, or 2 for hydrogen, make double bonds by taking a non-bonding pair and then double check your work. Okay, CBr4. So step 1, let's find the total electrons. So carbon has 4, Br has 7, and we have 4 of those. So we have a total of 32. We would think carbon will be in the middle. I'm going to connect all the other atoms with single bonds. And then we've now used 8. So we're going to basically count the rest and add them in. Or we could just go by saying we have 8 already. And then I'm going to add pairs to 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And we're done. Okay, that one should have been pretty familiar, right? How about the next one? This is going to be a new one. CO2. So carbon dioxide, right? Actually, what's the name of this one? CBr4. It would be carbon tetrabromide. Right? And here, carbon dioxide. So again, carbon each has 4 and is 1. Oxygen has 6 and there's 2. So 12 for oxygen for a total of 16 electrons. Now, what do you think is the central atom? Probably carbon, the one that there's only one of. So we will put carbon in the middle, make single bonds to the other atoms. And now we've used up 4 electrons. So we will distribute the remaining electrons in pairs around on the oxygens. So we have 2 and 4, 6, 8, 10, 12, 14, 16. All right, cool. So we used up all the electrons. And we're good, right? No, not right. Carbon. Carbon only has 2 bonds. So carbon needs 4 bonds. So we move to step 4. If any atoms are short of 8 electrons, make double bonds by taking non-bonding pairs. So here's a non-bonding pair. Here's a non-bonding pair. If we do that, we end up with this. And now everything is happy. So we're done. Notice that what we did not do, we did not do this And why not? So, electronically, right, it's all technically correct. But remember that oxygen is best when it has two bonds and two non-bonding pairs. Like we came up with the first time. And here, this oxygen has three bonds, and this one only has one, right? And also, there is some nice symmetry to this one, where it's the same on both sides of the carbon, and generally, symmetry is good and lower in energy, so we expect to see that with two double bonds. Okay, here's another question. Draw the Lewis dot structure for CS2. All right, I'm going to give you a hint. We just did CO2. And look at oxygen and sulfur on the periodic table. Think about the number of valence electrons and the dot symbols. They are exactly the same. If we take what we just did and replace the oxygen with the sulfur, we get CS2, right? The oxygen and the sulfur are completely interchangeable in the Lewis dot structures. So now the one that describes this, the central atom, is two double bonds and zero non-bonding pairs. So here's a note to help that we just used. Elements in a given column are the same in a Lewis structure. Like water, H2O, H2S, H2Se, oxygen, sulfur, selenium, totally the same. Additionally, hydrogen and halogens are the same in a Lewis structure, like H2O and OF2. The other example that we saw was CH4, and we did CCl4, CBr4, right? And they were all the same. Now, with the halogens had lone non-bonding pairs around them, and hydrogen didn't, but the way you put them around the central atom was the same. All right, so once you've done a few of these, you can kind of make substitutions, right? We also saw NH3 in this lecture, and we saw PCl3 in this lecture, and they were both the same basic structure as well, right? Okay, so that wraps up 3-4, and that actually wraps up all of chapter 3. In your textbook, on page 111, you will find all of the core concepts from each section. Starting on page 112, you will find all of the key words and terms from this chapter. And starting on page 113, you will find additional exercises to work on. And don't forget sapling and learning curve as well. All right, take care.